Okay, year 11. So let's do another physics one, shall we? Why not? And this is going to be all around radiation. So radiation is the middle of our bubble, and we will probably be doing this in class as well, but it's no harm to go through things again, or if you're looking at your mind map from lesson, you're not really too sure what that is written down, why it is, you can listen to my lovely tones and explaining why and what. So radiation, first thing, and this is an overlap with chemistry really, is isotopes. So isotopes. And basically, the definition of an isotope, and I'll explain what this means after, is the same element with a different number of neutrons. So it's an element that's the same, so lithium, it's got a different number of neutrons. So how will that look? Well, the lithium we found in the periodic table is like this, and an isotope of that is like this. So they're both lithium. The difference is, like we've just said, it's got a different number of neutrons. How do we know that? Well, we can do our little pen. Protons and electrons are the smallest. If you don't know this by now, you want shooting. So, protons and electrons are the smallest number. The difference between the two is how many neutrons. So over this side, your protons and electrons, with them being the smallest number, they are going to be the same. But neutrons, the difference this time is 3. So that is what an isotope is. If we're going to draw the difference, and let's quickly do that, 3 protons, 4 neutrons, and that's what that lithium looks like. And this lithium will just be different because it's still got these 3 pluses, but it's got 3 neutrons and not 4. Still the same number of electrons. Right. So, why do these exist? Well, these exist because every element in the periodic table mostly comes in different forms, in isotopes, and it just means one's more unstable than the other. So, let's now talk about the different types of radiation that you need to know about and that we come across. Radiation types. This is going to be in the form of a table. You know I love my tables where possible, and this is no different. So, we're going to have radiation types down here, so we have type, and we're going to have what is it? That's a question, of course. Stopped by. Ionizing ability, so ionizing, and then use. So this is our table. I haven't got a ruler handy, so I'm just going to do it roughly. Apologies. So, different types. First up, alpha. Next up, beta. Lastly, gamma. These are the 3 types of radiation. So for each type, you need to know what they are, what you can use to stop them, how are they ionizing, we'll come to that in a second, and what they're used for in real life. So what is it? Alpha is 2 protons and 2 neutrons. 2 pluses, 2 neutrons. 2 protons, 2 neutrons. Now that is the equivalent of a helium nucleus. Stop by. Well, if I wanted to stop alpha, what would I need? I'd only need a piece of paper. Or, I mean, air will stop it as well. It doesn't travel very far. It's massive in terms of radiation types, but it doesn't travel very far whatsoever. Now, because it's massive, its ionizing ability is high. It has a high chance of knocking electrons off, which is what an ionizing ability is. What they're used for? Alpha is used in smoke alarms. Beta then. Beta is the equivalent of an electron. So it's automatically size-wise, you can see that alpha is miles bigger than beta. An electron compared to 2 protons, 2 neutrons. Massive size difference. What do they need to stop beta? Aluminium. Ionizing ability, I'm going to put middle. I can't think of a better word to use than that, because it's always in between. And smoke alarms, not for beta, but beta is actually used for paper thickness. I'm not going to ever do that. What a stupid idiot. So I'm going to put a star and get that. Now those of you are neat would have hopefully avoided that error. So you can use beta to test how thick paper is, changing it accordingly. Lastly then is gamma. Now gamma is equivalent to just a wave, an electromagnetic wave. It takes a lot to stop. So you're going to need some lead to stop this bad boy. But because it's so small, its ionizing ability is very low. What are they used for? Well, they're used for sterilizing things. Sterilizing medical equipment. Because you get rid of all bacteria. Same as food. It's called irradiating food. So getting rid of all the bacteria on food. Giving things a longer shelf life. So these are the different types. Now, ionizing, I said we'd mention, and I'm going to. So it's the ability to knock off electrons. So what are these like in knocking off electrons? Well, alpha's the best because it's so big, whereas gamma is so small it doesn't do that much damage. So, don't forget, an ion is an atom that has lost or gained an electron. Right then, let's move on. Overall though, so what about radiation? What are the actual dangers? 2-mark question at the most. Can you recall 2 of these 3 points? Well, radiation will damage tissue. You can suffer radiation burns. Or they could cause mutations, and this is the one. When you get mutations happening, that can then lead to cancer. So that's why you would probably associate radiation with cancer, and that's how it comes about. So if it causes mutations in the DNA, then that could go on to become cancerous. Background radiation. So background radiation. So there's radiation around me while I'm writing this, and while you're writing that at home. But because it's always been there, we're used to it. So we get radon gas from rocks. Now these rocks vary up and down the country. So I'm going to put varies there. So depending where you live in the country, we'll be on different types of rocks, which will give off different types of radon gas. Food and drink. Cosmic rays, so from space. And also from the medical industry, so X-rays and things, and different scanning equipment will give off different background radiation. This is all these contribute to very low levels, okay, in terms of the radiation as a whole. And we do minimise it, especially in hospitals. The last thing I want to talk about with radiation is half-life. Now, the questions you get with half-life will always be accompanied by a graph. Half-life. So, radioactive isotopes So if you've got an element that's an isotope, it's radioactive, so it's giving off alpha, beta or gamma, it will decay. So radioactive isotopes are unstable and decay. Now this is where half-life comes in, and this is the whole principle of it. It will decay at a constant rate, a steady rate. And you can describe this rate by using a graph. And this is where you need to be able to work out half-lives from graphs. So you go 0, 100, 200, 300. Now this is not going to be accurate, is it? Because I'm just doing a piece of plain paper, not graph paper. I'm only doing it so you can get the idea. So up this side on the y-axis is radioactive activity. So how many clicks are you getting on your Geiger counter? And that is measured in becquerels. And you'll have time along the bottom. 1, 2, 3, 4, 5, 6. Could be days, hours, whatever it may be. And the question will say, calculate the half-life. And you'll get a line. Like this. You've got to use your graph to calculate the half-life. So, to start with, we had this piece of nuclear material that was 600 times every minute. Then after 2 days, so then what is its half-life? So from 600, we need to go from half of 600. 600, it was 0. 0 times 0. So half of that, 300, is 2. So its half-life is 2. Or you could do 300 to 150. Which doesn't quite work. It doesn't matter which one you take, as long as you take half. 400 to 200. It's better. So 400 to 200. So 400 to 200 is half. 200 is half of 400. As long as you take half, it doesn't matter. So 400, 200, half of. How long does that take? It should always be the same. 2. 2, 2, 2, 2, 2. The time it takes to half is always the same. And that is half-life. Okay, so you pick 2.600, half of 600 is 300, and you go across and read it, 2. That's the easiest way to do it. Okay, thank you for listening. Have a go at the questions.